All right, thank you for having us. Um, I'll start with an introduction here. You heard the title and you see our names there on the screen. We're going to use sport data as the title suggests, and we're going to try and build this graph model and talk about how the different hierarchies apply to our specific context. So we're either going to make sports really boring, or hopefully we'll make hierarchies somewhat interesting. Or maybe we'll do both. We'll see. Um, so here's our agenda. We'll start by the introduction, which I'll wrap up here in a minute, and I'll explain the context of our specific research. And then David will give a discussion of what are the problems that we're trying to solve here, and really it's related to hierarchies, as you've already discerned. And then he'll present our structural solution in a couple different parts. So the main outcome that you should be anticipating here is a solution that we use, a modeling solution. When you've got hierarchies that are at different depths, the data is dynamic, it's changing over time, but the history is also really important to represent within the data. The members, in our case, it's going to be sports clubs, are moving within the hierarchy over time. And then there's these other complex and unpredictable relationships that David will get into as well. So who are we? You kind of heard that we're university professors already there in the introduction, and you could see some of our background on the screen. But importantly for this presentation is we're co-founders of the Know Rivalry project, which is what we call our research project that's now spanned a little over 10 years. We've been collecting data on rivalry in sports, and the project itself is dedicated to fans' perspectives of these sports. So when you think about rivalry in sports, here you see the Derby of Milan, AC Milan and Inter Milan. As an example, Inter Milan wouldn't be the club that it is without AC Milan as its rival. And so there's a relationship there, and what we're trying to do, part of what we're trying to do in this project is represent these relationships across a lot of different geographic contexts and across a lot of different sporting contexts as well. And so what is a rival? Well, we've got an academic definition, but really the quickest and best definition is it's an opponent that has more meaning than other opponents that you might compete against. And you can have more than one rival as well. So that adds to our structure that we're going to consider here. The project, as I already mentioned, is Know Rivalry. If you want to learn more about the project, you can go to the project website where we've represented some of our data from fans. Again, we're looking at fans' perspective of rivalry. And the website is just knowrivalry.com. That's KNOW rivalry.com. And we're an academic research lab. And so we're in different locations. So our lab is somewhat virtual. And not only do David and I work on this, but we've got students that have been working on this through their progression. And occasionally we have affiliate faculty or other faculty that work with us on different projects as well. The data itself, the main part of the data from a primary research perspective is we're collecting survey data from fans, and we have over 50,000, approaching 60,000 respondents now that have completed our survey. But then within our data structure, we're looking to intermix that with secondary data, so that could be play-by-play data from games themselves. It could be sponsorship contracts that are based on rivalries or sponsors of specific teams. It could be TV ratings of some of these contests. And then, of course, the results of the contests themselves as well. All of that is examples of secondary data that we use. We're going to be talking about the context of sport, but really rivalry is one of those phenomenons that exists in many other contexts throughout society. Coke versus Pepsi, for example, or other consumer brands. Lowe's versus Home Depot is a big example of hardware stores with huge brands that are seen as rivals. The political context, here in the United States, we've got Republicans and Democrats, really a two-party system, which creates huge rivalries. There's also foreign relations as well. We talk about that quite a bit in my class and how that sometimes bleeds over into sporting contexts. And then there's workplace rivalries as well, where you get rivalries between employees or specific work units. So I'll turn it over to Dave here, and he will get into where we started in terms of a relational structure and how we took it from there.
All right, thanks, Joe. So the Know Rivalry Database is where we are storing all this, or KRDb, and that's what we'll use as the context for the talk today. It used to look something like this. It was a total mess, like so many relational databases end up being if you use them long enough. And we migrated to Neo4j, partly because hierarchies are hard. So that is the problem we're solving, dealing with the structure of our data, and hope that it can help with you. So to clarify, I don't like hierarchies. I didn't think I minded them until I started trying to model with them in SQL and query them, and it just became a hassle. SQL I think was just laughing at me when I was trying to work with it. Things are better with Neo4j with hierarchies, certainly, but there are still challenges. We have hierarchies, as just alluded to or previewed earlier, varying depths. You have the members of the hierarchies will move around. They will change names. They will change locations in the hierarchy, or they might exist in multiple places at once. We do research on 70 plus sport leagues around the world, and these are all structured differently. And that creates a variety of hierarchical builds, so to speak, and we have to try to develop a way to handle all those consistently. For those of you who aren't as familiar with sport, some examples here. This is the model of the Premier League, where you have a league. This is the top men's football league or soccer league in England. You have the league, and then you have the teams that play in that league. Okay, seems pretty straightforward. But the top soccer league in North America, Major League Soccer, you have the league, and then you have two conferences, and then the teams. So teams are nested under conferences, which is nested under the league. Then there's the NBA, which is the top men's basketball league in North America, where you have the league, the conferences, and then divisions, and then teams. So all these different levels. Of course, then there's American college football, where sometimes teams are nested under a division, sometimes nested under a conference, sometimes not at all, depending on where they are, such as the nature of a 100-plus-year-old sport. So that's one issue that we face, and you can think about this in your own context. With different departments have different organizational structures within the department, so this is certainly not an unusual situation. Also, members change over time. Back to the Premier League here. The way the Premier League works is the 3 lowest rated teams at the end of the season, they get relegated, which means they get kicked out of the league. And so for the next season, you have 3 new teams that come in. So every year, your league members are changing. Which, again, like if this is an organization, you have employees who retire or new ones join. So it's a very common situation to deal with. You also have members changing names throughout their time. The Delhi Daredevils used to be the Delhi Daredevils. Now they're the Delhi Capitals. The Montreal Impact are now CF Montreal. I'm not even going to try my terrible French pronunciation. I'll save myself that embarrassment. And then in Formula One, Racing Point, now Aston Martin. So these are still the same organizations, just different names. So when looking back at historical data, and as Joe mentioned, tying that in, bringing in the secondary data, we need to know what those names were at any given point, and that all those stats should roll up under the same organization. So that's a challenge. We can't just change the name on the node and move on, because then we lose that historical connection. Also, members move around in the hierarchy. Employees change offices, teams change locations. This is a bigger issue it's less of an issue in European football and stuff than it is in North American sport, partly because North American sport owners are much more profit seeking and get subsidies from taxpayers to move elsewhere, but that's a topic for another time. Then you have an issue where teams can be in multiple places in the hierarchy at the same time. So Paris FC, they play in the top level for French football, but they also play in the Champions League. And so they're going to show up multiple places at the same time under multiple hierarchies. And this is not unique to European football. In American college sports, the university, this is Brigham Young University, I'm using as an example here, they've got 21 sport teams. So you've got 21 teams that are nested under the university, but they're also competing in leagues. So they're nested under that league. So it's very common to be in multiple hierarchies at once. Now, you know, Neo4j, it does that very well. So, and partly I'm very happy why we moved to Neo4j, but it does create some challenges, and we'll see BYU again about some of its quirks. Okay, so how do we handle them? We're going to look at 3 different approaches. 1, creating instances of entities. I'll explain what that means. 2, building ephemeral relationships. Those are short-lived relationships designed to be created and destroyed regularly. And preparing for the absurd, or being creative and thinking of worst-case scenarios. First, creating instances of entities. What I mean by that is we create a version of each entity at a point in time, like a snapshot. For those of you who are familiar with object-oriented programming, you have a class, and then you instantiate the class. You create an instance of that class. This is the same idea. Let's take, for example, the Premier League. This is our node for the Premier League. We call our leagues KR leagues, like Know Rivalry leagues. So the IPL is the top cricket league for T20 cricket, and in our database, it's a KR league, and it also has the all ends tag, or label, which is the what we give these stable entities. So things like leagues and teams. And in cricket, or in the IPL, teams are nested directly under the league. So my first thought was this will be easy. Just, I've got some teams here. You can see those are some sport team nodes by Indians, LA Capitals, whatever. They're just nested directly under the entity. So I'm connecting these 2 entities, the team and a league, connecting them directly, nice and easy. Well, of course, it's never that easy. Realize that, well, teams sometimes come in and out of the league. A team might start and go defunct. Another team might join the league later. Okay, well, that's fine. This is Neo4j. Relationships are first-class citizens. This is wonderful. I'll just throw start and end dates on my relationships. Great. Now I can see when a team joins and when it either leaves the league or is defunct. And if it joins again, I could create a new relationship and it'll be fine. Well, let's look at this in a different context, and you'll start to see the problems here. You may already see them for this one. Here is David, hypothetical David. David is a student at UMass doing his master's degrees from 2004 to 2006. So there was a relationship created from David to the University of Massachusetts as a student from 2004 to 2006. Then David stuck around and did his PhD. So we get another relationship for doing 2006 to 2012. Okay, not too bad. Dave's a student, get a couple relationships there. This still works. But then David came back a few years ago as a faculty member. So now you have David, the faculty member, versus David, the student. And you can't put these, even though David already has a node, you can't throw the faculty label on that because David, the student, wasn't a faculty member and David, the faculty member, isn't a student. But you can't have two nodes like this because these are the same person and the database doesn't realize that. So to solve this, instead of storing the properties on the node, we can create store the properties on the relationship. We can create additional nodes in the middle between our two entities. And these are these intermediate nodes or our instances. So take, for example, our IPL league. The instance of a league, as we define it, is a season. So the 2022 season, that's a competition node. That's the label we use. And it has the relationship has recurring comp, which totally blatant stealing from the BBC's ontology. That was really helpful to see how they did it. Anyway, so the IPL has a recurring competition of a season. And so the IPL would have many of these seasons as we go back in history. So that's the season instance of a league. On the flip side, you have the team, Mumbai Indians, and they have an instance in that season, which is the 2022 Mumbai Indians. We call that a sports squad. So the squad is an instance of a team. The competition is an instance of the league. And these are the ones that get connected. So we're connecting the instances to each other to capture that point in time. And that's how we can see the path between a league and a team. Now, if this looks familiar to you, then you might have seen it elsewhere, such as in Wikidata. Wikidata, that's exactly how Wikidata works. You've got a team, like Mumbai Indians, you can see, instance of a cricket team. And then you have what we call the season squad, but for them, it's a sports season of a sports club. That's this Mumbai Indians in 2022. So it's the same idea. Or maybe you've seen this in a classic Mark Needham post. Well, all of his posts are classic, but a classic Mark Needham post on modeling football data using what he calls hyperedges, or what discrete math calls hyperedges, or intermediate nodes. And another example, where you might have seen this, great talk at Graph Connect in 2013 by Peter Olson from Marvel, talking about how Marvel uses hyperedges, these intermediary nodes, in order to model the relationships among all their characters. As Peter said in the talk, this is a fantasy world where anything can happen. People go back in the past, into the future, and have alternate timelines. How do you model that? It certainly makes it a lot easier. It puts my problems of sport data in perspective when I think about it that way. But this talk is excellent, by the way. If you haven't watched it, highly recommend doing so. It was transformative for me as I was struggling with how to model these data. This really helped. Where, use an example, you have like Hawkeye, the character, Clint Barton, the person. Well, sometimes Clint Barton's Hawkeye, sometimes he's not. And so you create these moments or these hyperedges or intermediary nodes to capture that. And we're using that same idea. So thank you, Peter. I'm sure you're not watching, but thank you for helping me understand this better. And I hope that this can help do the same for others. So that's fine, creating these instances, but what do we do with layered structures? Now let's remember the NBA. The NBA has two conferences, and those conferences each have 3 divisions. So that's our structure that we're dealing with, and the teams are nested under the divisions. We're going to just focus on this one right here, where we go from NBA to the Eastern Conference to the Atlantic Division, and just focus on that for a moment. So there are those same 3 nodes laid out horizontally. Again, there's our hierarchy. And we're just looking at one path along that hierarchy. We know that the NBA is going to have a season, but these conferences and divisions, they're entities as well. They also have the sport div label, where there's this organizational structure of a league, and they exist throughout time. They may or may not be part of the league. The NBA didn't always have an Eastern Conference, didn't always have an Atlantic Division, but we still need that node there. So we have instances of each of them. So you create those instances, and you can see that path has recurring comp. The NBA has a recurring competition of its season, and then that season has a substructure of the Eastern Conference's recurring competition and the Atlantic Division's recurring competition. So you have parallel paths working here. And of course, on the other side, we have teams like the Boston Celtics. They've got a squad. That squad is connected to the division season. So you can see a path from the NBA to the Celtics via these competitions. Notice there is not a direct path between the sport team and the sport div, the conference, division, league, whatever. Those entities, they do not have a direct connection yet. Remember, we tried that earlier and saw some of the problems with it. So what does this look like for Cypher? Let's take a quick look at the Cypher that would be used to pull this. Here's our league right there. So we're matching, we say the league, and I said NBA in this Cypher example, but certainly that could be changed. There are our instances, our competitions. So we're matching the league season, and it has substructures, maybe, of 0 to 5. We'll talk about that in a second. And season squads. Again, we'll talk about that. And I'm just filtering for a certain year. So that 0 to 5, the 0 is to handle flat structures, because in something like the Indian Premier League, which you can see on the left side of the screen, it just has the instance of the league itself. It doesn't have any substructures. So in this case, those two variables that I've put there, league season and season squad, those two competition nodes, in the case of the Indian Premier League, those are the same node, because there is no has substructure relationship. So that's why we have a 0. And then we have a 5 just because right now I have no, nothing deeper than 3 deep. So I figured, yeah, I'll put 5, allow me to grow a little bit. The way the data are structured, it really could be open-ended, but that's not a good database practice, and chances are I'm going to mess up at some point, and I don't want my data pulling infinite paths through my database. So that's why you put an upper end on it. And then we have the team right there, and the team, as we know, is connected via the squad. So we don't end up using these other two sport divs in the case of the NBA, or in the case of MLS, we wouldn't use the conference. We go directly from the league straight to its instance, and then follow that instance path, because the instance path is variable. You could go the other way too, but this is the way I've done it in this Cypher. Okay, so that works, but it's not perfect. It takes a long time to write this. It's computationally expensive to run this every time to get who's in the league. That's a very common thing that we need to get. So this is having to rerun this every time. It takes a while, even with indexing and whatnot. Also, there are even some functions that you can't use. I needed to use APOC convert to tree. Couldn't do it because I actually needed the entities. I couldn't do that with this structure as it was. So that's where we have ephemeral relationships. Again, these are short-lived relationships that are designed to be created and destroyed regularly. They are relationships between those stable entity nodes. So here we are actually connecting the league or division to the team directly. So we don't use the instances, we use the nodes themselves, or the entities themselves. These relationships are always created based on data that already exists in the database. So there's no original information on these relationships. They are just a convenient representation of data elsewhere. And they can be short-lived. They can be overridden at any time. So you should never count on finding them there, or finding them there, at least looking as they did the last time you saw them, because they could change at any moment. And typically you would want to have some type of saved cipher code that you ran either through a custom procedure, or if you've got it hooked up to Python and you run regular jobs or something. For a while, I just had cipher that I went in and manually did it. So you want to have something there that can destroy or update those relationships regularly. Now, there are downsides of these ephemeral relationships. One, you are adding storage space to your database. So that is a concern for some. And they are duplicating information, sort of. This is information that already exists in the database, could be gathered through queries, and may not be up to date if it hasn't been, haven't run the updates. So there are some things that you need to keep in mind here. So let's look at it with our sport data. Here's the path that you're familiar with. We have the IPL season, the team, and the squad. But instead of going on this circuitous path, we're going to create a relationship right here, which I call current subentity is. That's our ephemeral relationship. So instead of having to go all the way around, we now have that direct connection. The other connection still exists. This cur subentity is relationship is created by reading the other connections. It just does it in bulk and creates these cur subentity is to make for easier querying. In NBA, same thing. We lose all those green nodes and the yellow nodes. Again, we don't need any more of that because we are connecting entities directly. So cur subentity is, subentity is, and subentity is. You compare that cipher. This is what the cipher looked at like before, and here's what it looks like now. We're matching league, going down the path, and getting to the team, and then returning that. So we already talked about a few of the benefits here of ephemeral relationships. Another benefit, you can store information about the relationship on it, those properties, and that's fine, it's helpful. But what is also helpful for us, so I already showed the cur subentity is relationship. We also have ephemeral relationships for our rivalry research. Rivalries change over time. So we store aggregated data on the relationship. So for example, here is some of the data for what fans of the Mumbai Indians feel about rival Chennai Super Kings, where out of 100 rivalry points, they give 59 to the Canes, Super Canes. We have a Schadenfreude measure. Schadenfreude is joy at the suffering of others, 1 to 7 scale. You can see 91% of Mumbai Indians fans listed Super Kings as the #1 rival, and we can see when this was created. And there's the reverse, what Super Kings fans think of Mumbai Indians. And there's more here. I just included a few as an example. And this is nice. I mean, yes, we pulled all these data from the database. We could redo them. It is storing additional information that's already exists in the database, but it really makes things easy for our querying, because now we can very quickly, this is something we query constantly, is using these rivalry points. Now we have that right away in the database already stored. We don't need to go and check all the respondents and all their data and everything and redoing it. We've got it all stored right here. Makes it much easier. So those are the two most important parts about building that data structure to be flexible. The third part is kind of a little more fun, but smart, is to what I call preparing for the absurd, or the unexpected virtue of creative stress testing. Basically, we would sit down and try to think of the most bizarre scenarios that could happen, and then put our data to the test and see if our model would hold, and challenge our assumptions. For example, I assumed that a team's rival is a team in the same league. Here's the Wolfsburg team, And I assumed that their rivals would be from the Bundesliga. Well, that's not exactly true. They could be from the second level because their rival could have gotten relegated. Okay, at least it's still there. Oh, but then they also play in the Champions League. So their rival could be from a completely different country. When I realized this is when, this moment when I realized this is when I started thinking I've got to get out of SQL. So this assumption, nope, can't assume that. Another one, no team can exist twice in the same league system. Okay, well, this is Real Madrid. Well, so is this. Not technically the same team, but still kind of the same team because they've got the same parent club. This is the second, the reserves team. So that's something you got to account for. So that assumption's shot. If it's the same name, the same sport, it's the same team. I thought that one, okay, that should be fine. And not so much. Formula One, Renault is not Renault. They're both Formula One teams, both Renault, not the same team. Long story of why. Joe would be quite happy to answer those questions. He's the Formula One person. The Charlotte Hornets are not the Charlotte Hornets. You would think they are, but they're not. The old Charlotte Hornets are actually became New Orleans Hornets and then New Orleans Pelicans. New Charlotte Hornets were the Charlotte. It's a mess, right? This is the complexity. Also, we mentioned BYU earlier. I assumed university teams compete in university-based leagues. Seemed like a very safe assumption. In American sports, college and pro, they're completely different worlds. I know in English cricket, it's not the same, and I know it's in some of the clubs it's different. But in American sports, it's obvious to me. Well, for a long time, BYU's men's soccer team actually competed in a professional league. And so what I thought was a simple base assumption, shot too. So these are all sorts of challenges that we had to think about when building our model, and our model has been able to hold up against all this stuff that we've been throwing at it. So in conclusion, as you saw a preview earlier, modeling hierarchies is challenging, and through using instances of entities, ephemeral relationships, and creative stress testing, you can build your graph model in a way that can handle this and still make it easy on querying. I don't know if we succeeded in making sports boring or making hierarchies interesting, but appreciate you joining. And if you have any questions, you can please put them there or contact us afterwards through any of the means shown here.